When building a classification model, we have a couple different definitions of what a correct model means. We should actually be defining our goals for the model based on our use case and our domain expertise about the problem. For instance, if we're sitting down to build a nuclear missile launch detection system, we need to be really sure about the outcome before we take any action. We can't just be so sure before retaliating because we could start a war for no reason if we're wrong. In a different case, we're trying to detect pedestrians for a driverless car. We don't want to be quite as safe and secure as the detect nuclear missile launch use case because we want to hit the brakes as soon as we think it could be a human, and slowing down a couple extra times isn't actually that costly. Finally, maybe we're trying to detect what kind of bird is in a picture using some kind of visual learning method. We just want to get it right as frequently as possible, and we don't really care whether we guess a blue jay as a robin or a robin as a blue jay. As long as we maximize the number of birds correctly guessed, we're pretty happy. When we dig to the core of how to think about correctness, there's actually only 4 possible outcomes for every prediction. We compare the prediction to what actually happens, and we can either have true negatives, false positives, or true positives. So for a true negative, we think that some event does not occur and it actually does not occur. For the false negative, we think the event will not occur, but it surprises us and actually does occur. For false positives, we say, it's going to happen. It's probably going to be this outcome, but it surprises us and it does not happen. And finally, we have true positive, where we say the event will come to being, and it actually does. So for the nuclear launch detection case, a positive is missiles detected, a negative is all clear. So a true negative is we detected it's all clear and there is no attack. A false negative, we said it's all clear, but we're actually under attack. False positive is we say that we're under attack, but it's actually peacetime. And a true positive is we correctly detect that we're under attack. When you combine those 4 possible outcomes into ratios, we can derive a number of metrics that range from 0 to 1, where 1 is the best quality model for that particular dimension. The most basic is accuracy, which is the overall percentage correct. The number of true positives can be added to the number of true negatives, and we just take a look at that as a ratio of the total number. We don't necessarily care at all in this case about false positives or false negatives. For recall, we care only about the percentage of positives correctly identified. So we are looking at the true positive count versus the actually positive count, which is the combination of true positives and false negatives. For precision, we care about the percentage of positives which were actually positive. So we actually care about the ratio of true positives to the combo of true and false positives. And there's actually a number of other metrics as well which blend these factors together, including the frequently used F1 score. We'll discuss more about that in a following video, but the one important thing to take away from this slide is that when we talk about accuracy, it actually means something very specific and is not applicable to every single model. Going back to the first slide of examples, we can take those same examples through these 3 metrics again. When we look for the bird identification problem, it's not actually costly to guess blue jay or robin. We just want as many right as possible, so we are maximizing the true positives and true negatives count, and therefore we want accuracy. For precision, we're talking about the nuclear launch detection system. False positives are really costly, so we want a metric that actually takes that into account, and precision is the only metric out of these 3 which includes the false positive count as part of the calculation. Finally, for the pedestrian detection case, we're actually trying to have very few false negatives, and so we want to minimize the number of crashes into humans, obviously, and recall is the best metric for that situation. To take a look at this practically in a case study, we have this cancellation membership field for a particular churn use case for a retailer. For some business problems, we might want to start out with a very naive model where we are trying to detect cancellation of membership and maximize on accuracy. In this particular model, we're not prioritizing saving memberships. We're not maximizing on getting every single guest right. We just want to build the model that is right as frequently as possible and see what the top drivers are to begin my analysis. So when I pull out a particular model pipeline, I see not only do I have an accuracy number, but I can also see the precision and the recall for each of the classes. Even though my accuracy is very high here for this initial model, I actually only recall 37% of the trues, the churners, because they're actually a very infrequent population. When we use accuracy and try and detect a rare event, we might guess that it never happens and still end up 99.9% accurate. If we're actually trying to detect defections or churn as frequently as possible, maybe we'd actually want to jump over to the recall variable and maximize the number of people we can try and save. If we're trying to do a mass email campaign and try and activate people before they churn, if we're trying to do a mass email campaign where it does not cost us very much to contact the customer and we're just trying to prevent recall and we're just trying to prevent churn, we might go and maximize recall instead. And what we see in this situation is that we've actually lowered the precision down to 0.644 compared to an earlier precision of 0.86. But what we've gotten in return is a much higher recall value for true of 0.4 instead of 0.36. In a different situation, maybe we want to try and send out a really large gift or a large percentage promotion to customers, and we're going to maximize precision. I don't want to send this good offer to anyone who could possibly still stick around, and so therefore I actually want to make sure that I'm getting the customers who are almost guaranteed to churn and take those folks and give them a really rich offer. Then in that case, I might get to another pipeline which has much higher precision, 91% precision for churners rather than the earlier 86% precision or even the 64% precision. But in this particular case, I only have a 15% recall of true. This model, every time I say that they're going to churn, they're 92% likely to churn, but I'm actually only capturing roughly a sixth of churners. So I'm safely able to send these folks a nice rich offer, protect them, and maybe I would do a much less rich offer to a wider population where I'm maximizing on recall, but not necessarily very precise about it. The key when thinking about these problems is to actually understand what we're targeting from a business outcomes perspective, have that discussion with stakeholders, and then it actually should be very easy to retrain your model for the outcome that you're looking for.